turn things over to Nicola. Thank you very much for joining, Nicola, and we're looking forward to your talk.
Yeah, thank you, Chris. Thanks for letting me talk in this venue here, which I know is very popular in the community. So today I will talk about the some generic and local control on fault slip modes. And in particular, I will try to summarize together the research done in the raw mechanics laboratory at Durham University in the last maybe 5-6 years on this topic. And so I do have to acknowledge, of course, close collaboration with a range of people from Stefan Nielsen, Bob Olsworth, Telemaco, Chris Arbor, Fadul, the PhD student at Durham, and also some master students and undergraduate research students as well that contributed somehow in the research I'm going to present. So, okay, so there is essentially a very strong and broad, I would say, seismological and geophysical evidence that fault slip can manifest in many different ways during earthquakes. And in fact, from seismological data mostly and geodetic data as well, it has been identified now that there is a range of slip events beyond just the fast seismic slip of regular earthquakes. So we have low frequency events, very low frequency events, slow slip events, and so on. So it must be said that while it is still debated, maybe the scaling relationship between this different category of earthquakes, there is quite a general, I would say, consensus in the community that these type of slow earthquakes are somehow linked to observation of fluid overpressures, especially at subduction zones. And to help this seismological, let's say, idea that fluid overpressure plays a key role, there is also the help of raw mechanics, which provides also a mechanism for these slow slip events, which is usually the high latency hardening behavior when the pore fluid overpressure is released, cause some strengthening, which is slow down somehow fault slip. Now, it must be said that regardless of this, let's say, almost common acceptance, we have a much wider parameter space has been investigated, especially in the lab, by various raw mechanics lab in our community. And in particular, during this investigation of this large parameter space, many studies have shown that slip behavior, or the range of slip behavior, the spectrum of slip behavior that faults show from fast to slip, can actually also be controlled by other process and mechanisms. So what I call here generic controls are those mechanisms like fault healing, loading rates that apply in a quite generic way to every faults that are out there in nature. And then superimposed on these generic controls, there are also local controls which have been proposed by various groups listed here, including the work from Chris on fault stiffness. So these generic and local controls range from pore pressure distribution in terms of local control, fault stiffness, the role of fault roughness, fault zone rheology, and also some heterogeneous frictional properties of faults, which overall can determine this wide spectrum of slip behavior from fast to slow. Now, in this presentation, I will narrow the investigation to mostly fault healing, which we will use in our lab experiments. I'm going to present to actually modulate the slip behavior we observe from slow to fast. And then superimposed on the fault healing, I will also present the role played by fault zone rheology and heterogeneous lithology. I will touch very briefly on pore pressure distribution, showing a couple of slides with some experiments, because I think they are interesting in the context of what I'm going to present, but the focus is not on pore pressure distribution. In fact, most of our experiments I'm going to show you today are dry so room humidity experiments. So with this in mind, the experimental setup we used implies the use of a triaxial loading apparatus we have in Durham. And during our experiments, we used a range of sensors to monitor basic mechanical data like stress and strain curve, but also we use, for example, linear strain gauges across the fault zones to try to identify the timing and the amount of slip during, for example, in a saw cut during full slip. Also, we use some rosette strain gauges near the fault plane to try to work out the strain tensor and invert it to get shear stress acting on the fault. And then also we use piezoelectric sensors to monitor those fast events that are actually audible and can be recorded in the form of size of waveforms. So testing conditions during the experiments are relatively middle-low strain rate, 2 times 10 to the minus 4 seconds to the minus 1. And given the range of sensors here, the sampling frequency of our recording ranges from low frequencies to high frequency for some of the, for example, acoustic emission recording. And then we used, mostly I will be talking about saw cut experiments, and we use a constant surface roughening of about 400 grit throughout the experiments. So first I will, as I said, discuss the role played by friction and healing in controlling fault slip behavior. So we perform a range of simple, let's say, slide experiments on some westerly granite saw cut to start with. And the testing conditions were that confining pressure was kept constant during the experiment at around 50 MPa. Strain rate was, what I say, relatively mid-low strain rates. And then during the experiment, we had all times of 1, 3, 5, 10, and 15, 10 seconds. And then from 15 up to 50 minutes, depending on the nature of the experiment. So during the experiment, we measured the shear stress resolved on the fault plane, and here shown against time. And then you can see here how the different healing time in seconds first, and then in minutes. So slide experiments were run in a very traditional, simple way. So we had whole time, and then we calculated the healing by the change in friction observed after resuming loading after the whole time. And then we were loading the sample until basically we observed a slip event of some sort. And then the healing we derived from our experiments is something you would expect during for a westerly granite type of sample. So we have a power law. This is the best fit here when we plot healing versus as a difference in friction as all times. You can see that this is the classical power law scaling of healing with all time. So during this type of experiments, we basically observed 2 n-member types of slip event. So I'll start with what I call slow slip events. Usually they were observed for healing time of less than 5 minutes. And so these slow slip events, as shown here, one of them. In this case, we have shear stress versus displacement along the fault, resolved on the fault. So we can see after linear elastic loading, then we have the slip on the fault, which in this case lasts for a few seconds, maybe less than 10 seconds in this experiment. And at the same time, we could measure also the displacement. We can calculate the displacement on the fault plane during this slip event. Here we have the stress drop shown on this graph. Now, also, so this displacement here is calculated and measured from the LVDT located at the base of the column, but we can see the same event also from some strain gauges, in this case mounted just across the sample. So when the sample was slipping, the strain gauges would record the slip. Well, we record the strain and then we calculate the slip on the plane. So as opposed to these slow sleep events, we also observed some fast sleep events, usually for holding times more than 5 minutes. In this case, we have an event, a fast event, after 15 minutes. So the fast events, here we are recording at 0.1 hertz frequency. So we just captured the beginning and the end of the event in this case. And we can see a sudden stress drop and then also a sharp displacement shown here in the displacement graph. And then these events, the fast sleep events are usually, sorry, I forgot to say that for the slow sleep events, a constant characteristic is that they are silent, and also they are not recorded by the piezoelectric sensor. So that means that they do not radiate seismic waves, at least not in the amount that we can record in our system. For the fast sleep events, the main characteristic is that they are audible. So they are audible by us in the lab, but also they are audible by the piezoelectric sensors. And so they are recorded. And here we have the waveforms for this fast event recorded by 4 sensors next to the fault plane. Now, these are the fast events are actually proper dynamic events. So here we have we use the Rosette strain gauge sensors for one of these events to invert the strain for the stress. And this is mostly work of Stefan Nielsen and Chris Arbor, which was a PhD in our lab. So we can clearly see here on this graph where we have time in microseconds. So these are very fast dynamic event. We can see how friction, we are able to reconstruct the evolution of friction, which we have almost a complete dynamic stress drop in the friction. And then we also have in red here, the acceleration of slip during the event. And then we have some healing after, during the deceleration phase of the event. So if we summarize now the seismic parameters recorded by these events, and we plot the various seismic parameters versus healing, we can see that a very clear pattern here emerges from these experiments, which is that for relatively low amount of healing recorded during the experiments, we see that most of the events are silent, and then false sleep scales with healing almost linearly for the various events performed. Then when we get into the range of the highest value of healing, and these are usually attained, of course, for the longer hold times, then we see that a new pattern of events starts to emerge, which are these fast dynamic events shown in the graph here in red. So we don't see fast dynamic events in the low healing and short holding time during the experiment. We can also see that the stress drop for these events nicely scales as well with healing and tends to increase. So we have larger stress drop for the most dynamic event when we have the largest amount of healing. In terms of rise time, so the duration of the events, we can see that the duration of the events, of course, reduces with the onset of more dynamic fast events. Of course, the one plotted here in red are just the duration of the event is much, much shorter than shown here, because here we are recording, in this case, just at 0.1 hertz. So the characteristic of the slow events is that they have rise times between 12 and half a second. The slip velocity, as we reconstruct it, is less than 100 micron per second. And the rupture velocity also is in the range of 10 to 300 millimeters per second. On the other way, the fast event, if we see here on the slip velocity versus healing graph again, we can see that the fast events are much, much shorter. And the fastest, strongest event can be as short as 0.5 milliseconds. Slip velocity can be up to seismic slip velocity of meters per second. And rupture velocity scales well with the S-wave velocities of a few kilometers per second. So on top of the
Sorry, it's Chris. Just got a quick question. Can you you give us a little bit more information about what we know about the slip velocity in the audible cases? You said, because none of your points are over there, you just say the velocity is 0.6 meters per second. But you recording in some cases at a megahertz, right? So you must be able to see.
Yeah, so the most of these experiments, because there were like lots of experiments, Chris, we didn't use the rosette for all of them because it's quite so for those few experiments shown here in red, where we did have the evidence of either the piezo acoustic sensors to record the waveforms, or the rosettes to record events like this one, then it is from this observation here that we can infer a very large slip velocity on the event. But we did not use the rosette for every event because that is quite time consuming to do 30 experiments or so with the
Okay,
and we do know that the first event that we had the chance to look at and reconstruct, they are dynamic event like this one I'm showing here.
Okay, thank you.
Yeah. So then, as I said, pore pressure is not the main aim of this investigation, but I'm going to show you some experiments that we perform in a slightly different setting. So the one I just showed you is a room humidity SOCAT, traditional type of experiments. But then we also use two different configurations in our SOCAT. So one was where we were basically saturating the sample by diffuse percolation using an upstream and downstream porphyry pressure system we have. And then also another configuration was the saturation of the sample by direct injection through a borehole from the top part of the sample directly into the fault plane here of the SOCAT. So, and we performed for this type of experiment here, the diffuse percolation and direct injection of porphyry. We performed the same type of slide experiment as for the room humidity one I just showed you. So when we look at the results plotted in a similar way for this pore pressure experiment as the room humidity one, we can see, so the pore pressure here are the triangles, where the room humidity experiment, or a limited set of the room humidity experiments, are the crosses shown here. And also, so diffuse percolation are the triangles, but direct injection through the boreholes are the circles. So one thing, the first observation we can see from the stress drop, and then also the slip amount is plotted here, is that basically the use of porphyry pressure during the experiment somehow suppressed the occurrence of slow slip. So we didn't observe any slow slip events, but they were all fast, dynamic, and audible events. Then the second observation we can make is that also the amount of pore pressure, so we can see here 15 MPa are the open circle, for the direct injection 2 MPa pore pressure are the closed circle, and diffuse percolation we only did the 2 MPa pore pressure experiment. So we can see that the amount of pore pressure we injected seemed to control, at least for the direct injection, for example, seems to control the scale, the magnitude of the event, as we have larger event for the highest pore pressure we used. Also, another observation is also that basically it looks also that the mode of injection, or the mode of saturation, sorry, of the samples may play a role in, at least in these experiments, because when we add diffuse percolation injection, we had very, very large events, or much larger than the other methods of injection by the direct injection. And also we had very unstable behavior, so fast slip event for modest amount of healing. So then here, just cross-correlating the stress drop with slip amount for the diffuse percolation low pressure event, and also here the direct injection event, and the rise time, which of course these are all fast, short duration events. So it seems that the scaling between stress drop and slip amount still holds with the dry one, but these are just a larger, faster, more dynamic event with the pore pressure. So I'm presenting this data because then in a few slides, I'm going to present maybe to discuss a very speculative interpretation of what role may healing play. And so the presence of fluids may help somehow to support these interpretations. So in terms of the laboratory earthquake nucleation, then we were thinking about what may control this slow to fast events. And so we tried to play, for example, using a slip weakening model with the potential causes for the nucleation of this fast event and the manifestation of slow slip events. So if we use the, I think, Onaka classic slip weakening model equation here, we can see that we have a length of the fault which is 4 centimeters, and we can calculate the nucleation length using the slip weakening model based on the measurements and the data we collected for the slow and aseismic slip event and the fast and seismic slip event. So we can see that for the slow and aseismic slip event, the nucleation length scales almost with the length of the fault. So we are very close to the length of the fault, but for the most dynamic event, we can see that the calculated nucleation length is smaller than the size of the fault. So that may explain why, in this case, these events, were able to nucleate. So then, in a very speculative way here, this is really more maybe for discussion than actually assertive science. We start thinking about what is the role that maybe healing may play in terms of the controlling the sleep behavior of these events we observed. So when we have a smaller amount of healing, so this is an image here of the asperity distribution, the asperity distribution population of Westerly granite SOCAT performed by Chris in his published paper in 2017 in geology. And this is what we derived from profilometer measurement and then some modeling that Chris did. So we have a quite dispersed, if you like, small asperities along the fault surface. And then after a relatively larger amount of healing, we can see an evolution of the asperity population, and we start developing some clusters of larger asperities. So then our speculative interpretation here is that this large cluster of asperities may start to dynamically fail, and then eventually we can have a dynamic cascade up of small slip patches, and then they evolve in a larger slip patch, which is larger than the nucleation length, and so this can trigger a seismic event. So this could be the role played by, let's say, frictional healing in the range of experiments we run. And as I said, for the pore fluid experiment, it is interesting to know that actually in the presence of pore fluid or pore fluid pressure, we observe that this mechanism here, so the onset of fast dynamic slip was much more pronounced, much more effective. So that could be due to the role of fluids in causing or favoring, helping the plastic yielding of the asperities and somehow growing these slip patches on the fault surface. So,
Nicola, sorry. Can you tell us, in this case, perhaps I misunderstood. So are you controlling the roughness intentionally of the sample?
No, the roughness in the experiment I showed, the roughness is fixed with a 400 grit in all the experiments. because then, as you will see later, we would like to superimpose the role of lithological control. So I wanted something uniform so I could, clearly pick up what.
So this means that these two experimental setting here have the same roughness nominally.
Yeah, starting with, yes.
Okay, because yeah, I interpreted like due to the roughness. So interesting. Okay, thanks.
Yeah. But in Chris' work, actually, Chris did an investigation of the role of roughness. So he started with different roughnesses in the work. But in our experiment, we are keeping the roughness constant. So now we look at the core of our investigation, which is how the rheological behavior arising from lithological heterogeneities may eventually control the fault slip behavior. So in this set of experiments, I'm going to show you to investigate the role of lithology and rheology, fault rheology. We performed an additional set of experiments, which we started with. So the experiment I just talked about were just a westerly granite sow-cut experiment. So we added to this westerly granite sow-cut experiment some new experiments with a different configuration of the sample, and in particular a configuration that would allow us to investigate heterogeneity in lithology. So we did this by using composite samples. So a composite sample is made of, in our case, is made of a lower part, so a lower cylinder here, which is an initial sow cut. And then on top of the sow cut, we place some intact rocks, so some intact cylinders of rocks. And then so we could choose from westerly granite in this case. And then mostly we use coarse grain marble on the top. So this was allowing us to recreate some lithological heterogeneity and allow us to investigate as well the role of lithological heterogeneity and also different rheological behavior of the units on the propagation of the fault and the behavior of the rupture. So for these experiments, for the westerly granite, we mostly use a confining pressure of 35 MPa and the same values of strain rate. But for the composite westerly granite sow cut and marble experiment, we used a range of confining pressure because the behavior of marble, as I'll show you in a few slides, changes with confining pressure from brittle localized to distributed ductile mode of failure. So before I actually show you the results of the composite experiments, I would like to show you first some simple experiments we did to basically test that our results are not biased by the specific geometrical configuration we used in the samples. So the first thing we did then was the characterization of the intact samples we placed on top of the sow cut westerly granite. So in this case, we did some simple loading experiment to failure here for the marble we use. So this is an image of the initial material, which is a very coarse grain marble with some interlobate grains and low density of twins before the deformation. So we performed 3 experiments on this intact marble here at 5 MPa confining pressure, 10 MPa, and 35 MPa confining pressure. And as expected, we observe a brittle behavior with a stress drop and brittle localized failure for the low confining pressure. And then we started to observe a hybrid behavior at 10 MPa, where we had ductile failure here, followed by brittle failure. As you can see in the sample here, we have the brittle localized faults, but then also some intergranular fractures running parallel to the main fault zone. And then we have a ductile behavior at 35 MPa, so ductile mode of failure with distributed deformation by shear bands and also some barreling here of the sample. So this experiment defined the rheological behavior mode of failure of the intact marble we put on top of the composite samples. And then also, yeah, we reconstructed, of course, some failure envelopes using the Morse circles at failure, where we can clearly see a brittle mode of failure for the low confining pressures, and then gives way to a more ductile mode of failure at the highest confining pressure. So then we also, of course, characterize the rheological behavior and mode of failure of the intact granite, and perform 2 experiments here, 10 MPa in yellow here, and at 35 MPa confining pressure in blue. So we have the stress here versus strain curve. So in both cases, the behavior is very brittle, and we have a brittle failure envelope defined by the Morse circles at failure, and brittle failure manifests in the sample as well quite clearly. So then the final test we did to make sure that the, let's say, non-orthodox sample configuration we were using in this experiment was not affecting the results, was that we performed an experiment where we had a composite sample. So we had an intact granite, and on top of that, we had an intact marble sample. And then we deformed a 35 MPa to failure this composite sample. So the results clearly show here that after linear elastic loading, we have some yielding, and then we have ductile failure of the sample, which occurs, of course, in the weakest part of the composite here, which is the marble. And for reference here, these are the 2 end-member failure curves at 35 MPa for the granite and the marble. So we can see that the composite sample here behaves pretty much as the intact marble samples. And so this confirms that the coupling between the 2 parts of the sample here, it's very good. So then we can start seeing the results of the first composite sample we did here. With at the bottom here we had a granite saw cut, and then on the top we had an intact granite cylinder. So this is after the experiments what we observed in this specific sample. So this is the original saw cut, and this was the formerly intact westerly granite, which is now faulted by the propagation of the fault from the saw cut into the intact granite. So during this event here, we recorded 4 slip events, and the first slip event is shown here, was a slow, so slowish. I'll explain you in a second what I mean, and a silent event. So we can clearly see here that during this event, it started slowly here from the stress drop. So this is the shear stress. And then the stress drop was a little bit faster and more sudden. And we see the same in the slip along the foot in the sample that started slowly and then accelerated in the final stage. But this event was silent. So there was no recording of waveforms from the piezo sensors. Then we applied some healing as in the previous experiments, and we then observed another event occur, which is event number 2, which is again another slow event. So we can see the stress drop here recorded at low frequency, so we can see a few points. And then this is the slip, the net slip during this slow silent event. Then event number 3 started to pick up some speed, but was still on the slow and silent range. And we can see here the displacement as well. And then finally, by the time we got to the last event of the experiment, was slip event number 4, we had in this case a much faster and audible slip event. So when we look at when we put these experiments, so the composite sample experiment, which is sample number 284, which are the crosses in this graph here, in the context with the granite saw cut experiment we saw before, we do see that for relatively medium amount of healing, we had a silent event, and then we start moving into the more dynamic events. This is event, sleep event number 4. So in terms of stress drop and healing, these events in the composite sample look pretty much similar to the SOCAT experiments. So showing that the sample assembly we used, the composite sample assembly, was not actually playing a role in the end in terms of the nature and scaling of the events with stress drop, rise time, so the duration of the event, and also with the fault slip. You can see this is the composite sample compared to the SOCAT experiments. And the only thing that we observe is that there was an evolution as the rupture goes through from the SOCAT into the intact granite. So I took the development of the fault before the full instability could be developed for high manifest, so in a fast slip event with high amount of healing. So I'll show you some microstructures now that may help explaining us what was happening in the sequence from event 1 to event 4. So this image here is that we cut thin sections here at different levels in the sample, especially in the upper part which was initially intact, and this is where the rupture propagated through during the event number 1. So if we look at the fault characteristics very close to the contact between the SOCAT and the initially intact sample, we can see, and this is the step, you can see this is the intact sample, so this is the step. We can see very clearly that this is the fault plane, of course, but then very close to the edge here, we have quite a significant amount of fault damage by distributed fracturing at the junction here between the intact granite initially and the SOCAT fault. And so this is more likely what happened during the slip event 1. Of course, we also know that the slip event 1 was the one that entered into the intact sample first, because we have a very large amount of stress drop in the order of almost 30 MPa compared to just 1-2 MPa in the next experiment, in the next slip events I'm going to show you. So then we took a thin section as well at a much higher level away from the boundary here. And we can see that what we observe here is a very super localized fault plane with very little fracturing and damage outside of the fault plane. So this is a very sharp cut with very little fracturing. So we interpret that this is what the features of the fault zone with this very high localized super sharp fault plane are those that are more suitable for hosting a dynamic event like this one. So then so the previous experiment we had granite on top of, or intact granite on top of granite SOCAT. So it was like the rheological behavior there was homogeneous apart from the initial propagation of the rupture through the intact sample. Now we place on top of the granite SOCAT, we place an intact sample of marble. So the first experiment we did was at a very low confining pressure of 5 MPa, when we know that, we know that the marble behaves in a brittle way from the previous experiment I showed you at the beginning. So in this case, when we run the experiment, so this is what we had intact marble on top of the Western granite SOCATs. So this is the stress versus strain curve. So we can see that we had a very sudden stress drop, and this was a fast and also audible event, and we can see the manifestation of the fault here from the back and from here into the marble, which is very localized. It is actually a thin slip zone with very little fault damage, maybe some twinning next to the fault plane, but not much going on. So resembling very closely from a structural point of view to the fault, the sharp cut we saw in the westerly granite composite sample I showed you before. So then we to test the role of contrast in rheological behavior, we place another intact marble sample on top of the granite saw cut. But now in this case, we perform an experiment at a higher confining pressure of 35 MPa, where we know that the marble here should behave in a ductile way, as opposed as the brittle localized failure we see at 5 MPa. So in this case, the marble should deform at this confining pressure, should fail in a ductile way with distributed deformation. So this is the experiment we perform in this case. So we have shear stress here resolved on the saw cut plane versus time, and here we performed loading to failure of the sample first, and then we perform a series of slide experiments. So the first observation here is that during this type of experiment here, we only observed slow and silent events. So there was no evidence of dynamic failure occurring in the sample. And here there are the characteristics of one of these slow and silent event. So we can see here we have the friction coefficient versus time. So this is the shear stress. So we can see a stress drop, and then this is the net slip on the fault during this event. Then this is the structure we produced in the rock. So you can see the initial saw cut, and then the propagation of the rupture from the front, and then the back. So the propagation of the fault into the intact marble sample. So if we zoom a little bit more into one of these events, I think the one I'm showing you is the one preceding this one. We can clearly see that these are slow slip events. So in this case, it lasted more than 1 second. This is the stress drop we observed over just a few megapascal. And then we can see in this case that the amount of slip as well is shown here, and it's just 10 microns or so. And so also then we collected microstructural observation from the fault plane that we produced during the experiment, and we could see that in the marble. So we could see that the fault plane, well, there's not a fault plane, there's a fault zone. So it's a wide fault zone, which is clearly the marble failed in a ductile way. So it's a ductile mode of failure, which occurred by multiple slip surfaces, you can see here. And also there is quite some distributed damage by fracturing, but also twinning within the or outside of the main fault zone here. So in terms of the, so summarizing the data of the marble composite sample and putting them in context with those collected for the granite saw cut and also the composite intergranite and granite saw cut, we can see that for the granite saw cut, if we consider the seismic parameters of rise time, stress drop, and fault slip, we can see clearly that healing in this homogeneous lithology plays a role in terms of controlling the slip behavior from slow to fast for larger amount of healing, and actually having a composite sample but with the same lithology seems to produce faulting event which scale where the seismic parameters scale nicely with the more homogeneous case shown here. A completely different story emerges when we look at the composite sample, but where we have some lithological heterogeneity between the marble and the granite, and that lithological heterogeneity also results in a in a contrasting rheological behavior, because the granite saw cut is very brittle failure occurring, but in the intact marble, when we are at high confining pressure of 35 MPa in this case, the rheology is completely different because it deforms by distributed ductile failure. So it seems that the onset of this distributed ductile failure controls the behavior of the fault propagating into the intermarble, because basically suppresses completely the instability and the fast events, and only allows the manifestation of slow slip events, as we can see here from relatively long rise time. And then we have stress drop and full slips are similar to the previous events, but just it's a slow slip in this case. Of course, it's not only the lithology here that plays a role, because when we put the intact marble on top of the Western granites, but we deform the composite sample here at 5 MPa confining pressure, we have seen that if the marble behaves in a brittle way, then we still have a dynamic fast event propagating from the saw cut into the marble. So maybe going to some so let's say the key message here to take home is that the rheological behavior of rocks, which is controlled by different lithology in this case, clearly produce a different style of faulting, which results in a completely opposite slip behavior from localized faulting here, which is happy to host or produce fast slip, to more distributed slip and damage, which results in more slow slip characteristic of the fault. So in terms of some discussion point here, I would say that these results may have some potential implications here, in particular in terms of understanding how lithological heterogeneity in the upper crust, which is very common, as many earthquakes, many seismic sequences in nature cut across a multi-layer of rocks, from basement rocks to sedimentary rocks with different, of course, mechanical behavior and also geological behaviors and mode of failure. So these experiments suggest that lithological heterogeneity in the upper crust can produce some contrast in rheological behavior. So, for example, brittle versus ductile behavior, as we saw for the marble experiment. And this contrast in rheological behavior may actually result or produce a range of fault slip mode from slow and seismic to fast seismic slip. So in this cartoon diagram I showed here, we can see how if we use a more maybe realistic rheological profile or strength profile of the crust, and usually the one with a straight line for the brittle crust, which is assumed based on the rheology of quartz. So then if we use a more realistic one, which accounts, for example, for different rheological behavior, in this case, for example, ductile failure in carbonates or other rocks with similar properties, then in that case, we can see that maybe the presence of these rocks at depth and their contrasting rheological behavior could actually result into different rupture behavior, for example, or may result in seismic sequences which are actually more complex than, for example, large earthquakes able to nucleate close to the brittle plastic transition, then propagate upward through the entire crust. So, for example, the presence of ductile or rheological behavior with ductile failure in some sediments at some point at depth in the crust could, for example, cause the arrest of the rupture, which is like in our experiment, is not able to propagate fast into these ductile sediments. And for example, as well, the loading or the aseismic failure in a ductile manner in portions of the upper crust may also be able, for example, to load the shallower portion of faults. So from a seismic hazard, this has potential implications because it may control the size of the earthquake, but also the evolution of rupture propagation and also the complexity of the seismic sequences, as we know that there is no one single earthquake that is the same as another one. So to conclude, this has also been, the role of lithological heterogeneity and contrasting rheological behavior has also been recently investigated and shown, for example, by Cristiano in a recent paper published in Nature Communication, where basically it was shown that in the northern Apennines of Italy, here we have a map view of the northern Apennines of Italy, just before and after the Norcia seismic sequence in 2016 and 2017, there was so the seismic data shown here and the geological cross-section shown here at the top are from a transect orthogonal to the main extensional faults shown on this map view here for the Apennine. This is the Norcia earthquake, and this is the Amatrice earthquake, and this is the Visso earthquake during this 2016-2017 sequence. So it has been shown that during this seismic sequence here, a significant amount of seismicity, for example, was observed within the Triassic evaporites. So, for example, these clusters of seismicity shown here and there, cluster 1, 2, and 3, but also significant amount of distributed seismicity was in the Triassic evaporites was present in the hanging wall of the Norcia fault, which is the fault that hosted the main event in 2016, a 6.5 magnitude event. So it is interesting to know that these Triassic evaporites have a behavior, for example, very similar to the marble we tested in the lab. So they undergo ductile distributed deformation at confining pressure in a larger, equal or larger than 40 MPa, so relatively shallow depth. So what was observed in this case before the event with these clusters 3, 2, and 3, the main event on the Norcia fault here, and also after the main event here down in the hanging wall of the Norcia fault, that there was this significant amount of distributed seismicity, which resulted in a very complex seismic sequence here where we have localized major earthquakes along the main fault, but then also large volume of seismicity with lower magnitude in these Triassic evaporites here. So it could be, for example, it was suggested by Cristiano, and this is why well in context with the experiments I just showed you today on marble with similar rheology. It could be that this contrasting rheological behavior that we have in the multi-layer here of the northern Apennines between basement rocks, brittle carbonates, and maybe ductile evaporites may likely have control as well the complexity shown here by the seismicity during the 2016 and 17 seismic Norcia seismic sequence, and in particular may have control, for example, the rupture, nucleation, and propagation, maybe arresting the rupture just before entering the Triassic evaporites here, which are actually quite deforming by distributed seismicity rather than localized large events. And also, so may have also controlled, the complexity, but also the rupture behavior during the seismic sequence. And I think I have finished here. Chris?
You certainly have another minute or two if you'd like to summarize, but
Yeah, so the key, I think the key message to take home, I would say, from these experiments is that maybe mostly for continental environments than subduction zone, but also in subduction zone we have heterogeneity in lithology, is that many earthquakes propagate through a multi-layer of rocks, which range from basement, hard basement rocks to softer, sediment rocks, and every rock type, every lithology, it's characterized by its own rheological behavior, which is controlled by, for example, effective pressures, or pore pressure may play a role, or confining pressure may play a role. And that rheological behavior results in a style of faulting, which may control the slip behavior on faults. So, for example, if you have a very brittle rheology, like the shown by the westerly granite, SOCAT experiment or composite experiment, then those rocks and their mode of failure are actually quite suitable for the propagation of fast earthquakes, as we know most of them. On the other hand, if you have a multi-layer where there is a significant thickness or presence of rocks which have a different rheological behavior at depth or even shallow depth, then the mode of failure and the style of faulting in these rocks may actually affect rupture behavior, and also the complexity of the seismic sequence, because maybe slip may manifest in different ways, as we saw in our experiment, than just fast slip along localized faults. But you may have the onset of slow slip events or less efficient propagation of the rupture through this rheology, where you have more distributed fracturing. The cause of this could be that it may take more energy to propagate rupture through a distributed mesh of fractures or faults than keeping it localized along a narrow fault, of course.
Nicola, thank you very much. That's a fabulous talk. Is there another slide, or you're finished?
Yeah. Shall I exit the presentation mode?
No, as you like. You could go into just showing your slides without being in presentation mode if you'd like, but
oh yeah. So it would be a little bit less.
As you like. Just like to invite everyone to join me in thanking Nicola for a fabulous talk. Really, really interesting. Lots of interesting things, Nick. Yeah. And while we let him catch his breath for a second, the reaction button at the bottom of your screen is a good way to put ourselves in some order to ask questions. I've just raised my hand for fun to show you how to do it in case people don't know. I suppose everyone's an expert, but yeah, just invite people to raise your hand and join the discussion with some questions of any sort that you'd like to ask. And Brad Hager, please go ahead. You're still muted, Brad.
Yeah, I got it. Okay. Thanks very much. That was a very interesting presentation of some really fascinating experiments. I'm taken by the contrast in structure near the fault in your last experiments, where you had a fracture in the lower block going into an unfractured upper block, and you had off-fault damage near the boundary, and then a very clean fault break up near the top. And also it looked like the fault plane itself was rotating between the two samples, so the two regions. So my question is, what's different about the stress or the strain or whatever in the area where there's off-fault damage and the area where the fault is very sharp? What's the, what do the rocks locally feel in those two different environments so that they behave differently?
For the stress field, do you mean the so to infer the stress field like in nature, or because
so I mean I'm talking about your lab results. So you have you have different orientations of the fracture in the region below and the region above, and you have different distributions of off-fault damage near the contact and far from the contact. So I'm just wondering what causes those variations, particularly in off-fault damage. Why does it decrease as you go away from the fault, from the contact?
So the maybe to clarify that, I don't know, I can go maybe back to the slides, it would be easier.
Yeah, I think it's a good idea, Nicola, just to share your screen. Even if you don't go into presentation mode, we can just
Okay. It's still in the presentation mode, but that's okay. So the
you can drop out of the presentation mode and just into a mode where you're showing us one slide at a time. Yeah, that's right.
Is that okay?
But now You have to bring back your PowerPoint. We're looking at the email right now.
Okay. Here is the email.
Yes, yeah, now
Okay.
it's,
Yeah.
yeah.
All right. So the I think the what we see here, so very close to the boundary between the sow-cut and the intact westerly granite, is I think this is very localized, and you know, we don't see, as soon as we move away from this portion here, we don't see, you know, these features in the granite sample anymore. On the other hand, when we look at the carbonate sample, we do see this distributed nature of the faulting all the way through from the bottom to the top. So I think what I think happens here, but it's maybe hard to tell, is that when the fault wants to enter the intact sample there, of course, there is a lot of stress concentration happening here, I think. And the rupturing here could be easily the shattering of the rock with the rupture, when the rupture enters in the sample and breaks the intact rock. But I don't think it's a feature of the fault itself, because with the other slip event, as the fault is aptly already formed, these are more, I think, slip event that tend to occur on the main fault plane away. So I think this is just a local effect, in this case for the westerly granite, of the dramatic entrance of the fault into the intact rock, when we have a lot of, I think, elastic strain stored in the intact sample.
Okay, if I can just ask one more question and related to this, and is the fracture propagating upward in multiple events, or does it all slip at once and the whole upper block slips from the very beginning?
I think that the fracture propagates. It's difficult to say whether, you know, after slip event 1 has already propagated, but we did some experiments where we only had one slip event to test. This is what I wanted to test, whether after one slip event, and we could see that the fracture was propagated up to the end during the first slip event. Then, of course, maybe with the subsequent event, then of course you have more slip and maybe it gets more mature. I don't know, but the fracture manifests itself already during the first slip event, almost to the end. And we could also see this from the strain gauges, which are orthogonal to the fault. So the aim was that one as well, to see whether we could see slip from the first events. And so the strain gauges and the observation of shorter experiment with one slip show that the fault developed as it is in the intact rock from the very early stages.
Thank you very much.
Yeah, Nicola, really a fabulous talk. Thank you. Encourage people to raise their hand, join in the discussion. And Paul Johnson, go ahead.
Thanks, Nicola.
Hi, Paul.
Really super interesting talk. I find the difference in the rheologies have a really profound impact. I mean, you might expect that, but maybe not to the degree you've shown us. In the slide we're looking at right now, that you and Brad were discussing, is it my imagination? But on the right-hand side of the fault, is there distributed damage throughout that volume, or not? It looks to me like it could be.
Yeah, this one is so this is the granite on granite, so a very brittle, rheology. So we are close to the edge again between the sow-cut and the intact. And here, yes, we do have a localized, just at the bottom here, we have a localized distributed fracturing and no fault damage here, which it could be well the result of the early slow slip when the fault is starting forming and propagating into the granite.
Okay.
But
that
then
was the
as
question.
we move upward along the fault, then the fault looks completely different, because it looks a very straight fault plane with not much of fault damage in this case for the upper section. It's just very localized here at the interface where I think you have the highest stress concentration, because you have to consider that in this configuration here, from a mechanical point of view, we are very heterogeneous condition, because we have that the amount of stress required to reactivate the socket, yeah, is less than the amount of stress needed to break the intact granite. But nevertheless, the intact granite is broken and the socket managed to slip. So that means that here, I think, at the interface where, yeah, you have a lot of stress concentration, almost acting like a notch, I think, too. Yeah.
Okay. Really interesting. Thanks a lot, Nicola.
Because the stress level in the intact is well below the one required to break an intact sample of granite. So this is a dynamic propagation of the rupture in the granite.
Yeah, I wonder,
Okay.
following up on that, Nicola, if so, if you did this in a much stiffer system that either didn't allow or minimized the dynamic nature of the slip on the saw cut, would it still work like this, or even if you?
Yeah. If actually I finished quite early, but I thought I had lots of stuff to say. So I took out a slide where we did a rock which was strong, a composite saw cut with a rock that was stronger than the westerly granite, because the marble is softer, the westerly granite is the same. And then we use a westerly granite saw cut, and on top we use the Rivenhorn basin shale. You know, surprise, surprise, the shale was stronger than the granite. It's a very stiff rock with the facility orthogonal to the rock. So what we observe in that case, I might have a slide I can show you. And in that case, I also have a movie with the acoustic emission showing how the rupture propagates. So in that case, you have to trust me by faith, but I can recover the slide. So what we observed in that case with a stronger lithology, Chris, was that we have a little, let's say, hip into the hiccup into the mechanical data showing when the saw cut started moving, and we saw some microseismic events along the saw cut, but the rupture couldn't go through the much stronger rock. You know, the saw cut couldn't go. So what happened at that point? It kept loading then elastically again, and then we had the development of a conjugate fault, yeah, into the intact saw cut. So broke first the intact saw cut, and then that fault was able to propagate into the shale, and we could track the propagation with the. I think I can show you. I think I have. Yeah. I prepared this slide because I thought maybe it was going to.
Thank you.
It's another presentation, so it's. Yeah. So can you see the?
Yes, we see it. Yep.
Yeah. So without going into the details, so this is a cyclic pore pressure fluid. You know, this is a complex experiment. But to go straight to your question here, so can you see here on the left, on the right hand side?
Yes.
So this is the initial saw cut. So we have the initial saw cut is here. Sorry, no, the saw cut is here, pre-existing fault. So that's the saw cut. Yep. And then we have this shale rock on top, which is stronger than the westerly granite. So then we started loading, and in the mechanical data here, you can see this little stress drop. I think from the we can see from the acoustic emission location here, you can see this is the beginning at this stage. So this is the first slip event. Maybe I can put this bigger. Can you still see it?
But we're in a mode where we're seeing a different kind of presentation mode. We're seeing not just your slide. I could see fine.
So, okay, so this is the activation of the saw cut in the granite first.
Yeah.
And we have this acoustic emission here on the fault plane, but then it got stuck, had no penetration into the shale, and then so it kept loading, and then when we have the stress drop, when the
I see the conjugate
up, and then we have the formation of a new fault, which is this new fault in the westerly granite. So the system goes stuck here, then we have the new fault, and then with the new fault, we have all the microseismicity, which is progressively propagating into the shale.
I see. Yeah.
So it's not only the rheological conscious behavior in this, at least from this experiment, but it's also actually the strength of the rocks which may play a role. And in this case, we have a much complex fault pattern and a much complex seismic sequence in lab earthquakes than the westerly granite examples I was showing before.
Yeah, it's really interesting. Thank you. Okay, now I'm going to stop the recording right now. So for people who would like to ask more private questions, please, this is the time. And I see we have Vitzal and Massimo. So Massimo Coco, go ahead, please.
Ciao, Nicola. Thank you very much for the presentation. So did I